So you're watching this video because you want to know more information about this horrible spreadsheet that's going to happen with fractionation. Well, I'm going to have to say, it might not be horrible, it just looks like a lot of information, and it is a lot of information. So a part of the process here is trying to order the information in a way that makes sense. And for some of you, especially if you've not used Excel that much, you're actually going to find a bigger problem trying to order the information than to actually do the calculations for the lab. And that's the purpose of this video. So what I want to show you with this video is my spreadsheet and the way that I've ordered mine. By no means do you have to copy this. By no means do you have to make a replicate. But it will give you an idea of what type of spreadsheet, where the numbers should go, what type of calculations should be ordered, and maybe the overall objective of the calculations and the spreadsheet involved in the fractionation lab. So what you're seeing on the screen is a master spreadsheet that I have listed here in the very first column, the fractions that I have collected. Now, my spreadsheet is a master spreadsheet, so I don't really know if you've collected 12 samples or 14 samples or 20 samples. So you really just have to put however many you collected on this spreadsheet, and that's it. So I've went all the way up to 20. I can make this spreadsheet bigger. I can make this spreadsheet modified in order to make it work with your samples. But for you, if you only put 14 samples in, put 14 samples into the spreadsheet. We're good to go. All right? So that's what's going to be in the first column. In the second column, this is the refractive index reading. So as you can see all the way through the screen, I've included the refractive index reads, and I've kind of split them up into two portions. And I'll talk about those portions in a minute, but that column is for my refractive index. And we know that that refractive index is going to require a calculation, and that calculation is in the lab procedure, and it's also part of the pre-lab questions. So you kind of know what's going to go on as far as the math is involved, but the second column is refractive index read. The third column is the number of milliliters. So the number of milliliters that you collected for that particular fraction, that's what's going to go here. For the most part, most of you are recording to 2 decimal places, and you're probably not going to give me any weird numbers like this person did of like sample 14, 2.77. But you probably are doing 2.70 or 2.75 or 2.80. You're probably rounding it off that way, which is okay. But you should have been collecting in a graduated cylinder. That graduated cylinder should have had a recording about the volume, and because of that, those volumes go into the spreadsheet. We need those for the calculation. All right, so the next part of the spreadsheet is going to be this percent of acetone, percent of cyclohexane, and the percentage of toluene. And this is really where the two divisions happen. Because if you look, the first section, in this case 1 through 6, is giving me acetone and cyclohexane. But there's no toluene here yet, right? The boiling points are too low for toluene to come over. Toluene is still over in my boiling flask. It's not basically been into the condenser yet. So I'm assuming a 2-component sample, and that is it. The second half down here at the bottom, this half represents the latter part of the fractionation. So if you look, there's no acetone here because at this point we're going to assume that all of it is off. And then the 2-component system turns into cyclohexane, which is the one smack dab in the middle, and it turns into toluene here. Notice the generalization that goes on as we continue through the fractionation process. So the percentage of acetone, it looks like it starts really high at 73%, and it goes lower, 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 and then bam, it's gone, right? These numbers are kind of all over the place, 73, 76, 75, 77, 79, but they should kind of go lower and lower as you migrate through the spreadsheet. If you look at cyclohexane, the same kind of thing is going to happen here. You're going to see cyclohexane starting off really, really low, and then it will gradually creep up. For the most part, it will gradually creep up. So 26, 23, 24, 20, 20, bam, 90. Then 91, then the 80s, and now it's going to go lower. 20s, 4, 1, 1, 1, 1, 1, 1, all the way down. Well, again, cyclohexane's in the middle. So what's happening is that as the sample is heated, acetone's being driven off first, and the concentration gets lower and lower throughout your fractions. Then cyclohexane's going to make an appearance. Cyclohexane eventually is going to show its head, so we'll see an increase in the concentration. And then eventually cyclohexane is going to be less and less because there's only a certain amount of it, and that concentration will actually start to go down because we're distilling all of it off, right? And then finally for toluene, toluene's not coming off in the beginning, so those concentrations are super low. We're just going to assume 0. And then as toluene begins to fractionate off, it starts off at a really low concentration, but then after that, the concentration goes up and up and up and up all the way to the very end. So that's the generalization that you can take away from the fractionation process. Now, how do I know how to separate these two blocks from each other, right? So samples 1 through 6 were separated from samples 7 through 18. And why did I make the division and why did I do it there? Well, there's going to be a point here where you will do a calculation, and that calculation will give you a negative concentration, and that doesn't really quite work. So I'm just going to pretend for a moment that vial number 7, I'm just going to type in as part of a acetone cyclohexane mix. So 4.190, okay? So if I do that, well, sorry, let me change that. That was vial number 6. Vial number 7, 1.4313, right? That was the refractive index that we used down here. So if I plug that 1.4313 into the general equation for acetone and cyclohexane, and I hit enter, what you're going to see is a negative percentage for acetone when you do your calculations. Well, that's a problem. We know that we can't have a negative concentration, right? That makes no sense to us. So because of that, that's a very good sign that that sample container number 7 no longer contains acetone anymore. So because of that, I just in my spreadsheet did a division. I separated into 2 sections, and the second section now is going to represent my other 2-component system, which is cyclohexane and toluene. So my advice to you is that when you do these calculations and you plug them into the spreadsheet, when you get to the point of a negative concentration, get you some extra space in between the 2 blocks. That way, when you go through and do the next calculation that we're getting ready to talk about, you won't get confused and you'll be okay. All right, so that's where my acetone becomes negative. That is a very good sign or an indication that this no longer is an acetone mix anymore, but it needs to be changed to a cyclohexane and toluene mix. All right, so I'm just going to go back and I'm going to delete these 2 numbers. And the next calculation that we need to talk about are the milliliters. So here's the thing. This is why you have to record your volumes throughout the fractionation. Once you use that equation that's in your lab procedure that you've also used on the pre-lab quiz to calculate the percentage of acetone in this first sample and the percentage of cyclohexane, you then need to go through and calculate the number of milliliters that is related to. So how do I do that? Well, look. Here you've recorded 2.98 milliliters of sample, right? So in the first container, you had 2.98 milliliters. And you're telling me, based on the spreadsheet, if I pull that up again, that your acetone is 73.33% of that total. So 73.33% is acetone. And then you're turning around and telling me that 26.66 is going to be your cyclohexane. So 26.66 is your cyclo. All right, so this is what we need to do for those columns. In order to calculate the actual number of milliliters contained in those fractions, well, you need to take your volume, that you have said that you have received in that fraction, and you need to multiply by the percentage. So here, 73.33%. So you need to take 0.7333 multiplied by 2.98, and that will give you the number of milliliters of just acetone that's contained in that fraction. You'll then do the same thing for cyclohexane. So you'll take 26.66% of the volume that you've collected, and that is related to the number of milliliters of just cyclohexane that's inside of your sample. And then you're going to tabulate those numbers all the way throughout the spreadsheet. So what you're seeing is that for here, to get the 2.19, I took the 73.33 divided by 100, so I could turn that into a decimal, and then I multiplied by C5. And C5 is the total number of milliliters that I received in that fraction cut. So that gives me 2.19. Then I do the same thing for cyclohexane. The mils of cyclohexane is 0.795. So you follow that trend all the way through the spreadsheet into the very bottom. Notice in the second half, these are just going to be zeros because you're going to claim that no acetone was collected in these fractions at all. And then down at the bottom, you're going to see a component total. And what this component total is a summation of all of the milliliters of acetone that you have collected. So I've basically put sum of E5 all the way down to E28. But you do whatever is right on your spreadsheet depending on the number of fractions and the lines that you have. The same thing happens with cyclohexane. I do a summation once I do the percentages, and once I do the calculated for the mils, I add all of those numbers up in every single cut, and I get a total. It just so happens to be 17.1. And then the same thing happens with toluene. So with toluene, you're going to take all of your fractions and you're going to add them all up based on those calculations, and you'll get a total of 18.9. Again, notice that toluene is not coming over in the beginning, so those volumes are going to be 0. All right, so we actually know how much we put into your sample when we gave it to you, and it looks like the actual numbers here should be 10 mils, not 8, 20 milliliters, not 17, and 20 milliliters, not 18.9. So this gives us a very good indication of how well you collected your fractions and how well you were able to separate your fractions from each other. So over here to the right-hand side, this is where I've put the refractive indexes for each one of the pures because we need that for the calculation. So I'll just go ahead and enter it into the spreadsheet over to the side. The total recovered, this is how many milliliters altogether that you have collected from the fractionation. So this is 8.03 plus 17.1 plus 18.9, and that goes there for total recovered. And then to calculate that percent recovery, what you would do is that you would take 44.0, which is the total amount that you collected in the fractionation process, and then you're going to divide it by the actual total that we provided you. And in this case, 20 plus 20 plus 10 is 50. So 44 divided by 50 times 100 will give me a percent recovery. So it looks like this person has lost about 12% of their sample. And part of the problem is, where does that 12% go, right? How did you lose 12% of your sample throughout the fractionation process? You could probably use a little bit of common sense to answer that question, but that's what that's for, all right? Then you're going to see a whole section down here that says percent of acetone RCVD. That means recovered, all right? Percent of cyclohexane recovered and percent of toluene recovered. So the recovered basically is based on your total amount that you recovered from the fractionation process. We know that you're going to lose some. So what happens is that we're going to have two different paths of calculations that happen here. One is going to be based on your recovered amount that you retained in the lab. The other one is based on the original amount that you should have gotten from the lab if everything worked ideally. And that was off of 50 milliliters in this scenario, right? Because we're telling you, you should have had 20 mils of acetone, you should have had 20 mils of cyclohexane, and you should have had 10 mils of acetone. 20, 20, and 10 is 50. So this section is based off of the 44 milliliters that this person recovered from the fractionation process. And then this section is based off of the original volume, which should have been 50 milliliters in total. Okay? So basically what happens is that I know that the acetone here, the percent of acetone recovered, I took E30, which is 8.03 mils that this person received from the fractionation, then divided it by M9, which is the total recovered of 44 mils, times 100. And that gave this person, let me go back, 18.3%. All right? The percent of cyclohexane recovered, same kind of deal. You take 17.1 because that's what you got. Then you divide it by 44 because that's how much you've recovered, and you multiply by a 100. And then you do the toluene the same way. So take the amount of toluene of 18.9, divide it by 44 times 100, and that gives you 42.9%. All right. Then you do the same thing for the original. The difference, though, is that these numbers are based, again, off of what you should have received. So for this calculation, you would have taken the 8.03, and instead of dividing it by 44, which is how much you recovered, you divide it by 50 here, because that's how much you should have recovered. So it's based off of the original volume that we provided. And you're seeing that that percentage goes down a little bit. And that's pretty much common, right? Because you're not going to collect all 50 milliliters. You're only going to collect a certain portion of it. When you involve the 50 mils, these percentages tick down a little bit. Cyclohexane's the same way. You take 17.1, but don't divide it by 44 this time. You're going to divide it by the 50 that you should have gotten. And then the percent of toluene done the same way. 18.9 divided by 50 multiplied by 100. And all of these percentages, again, will go down slightly. All right. Now, the percent of acetone, the percent of cyclohexane, and the percent of toluene that's here on the screen, this is the actual percentage of what it should be. All right, so we know what we put in there, and we know the total volume that you started with, and that's how we calculate this percentage. So what we've done to get these numbers is that we have taken 10 milliliters of acetone divided by 50 times 100, because this is how much acetone you should have had in the 50 ml sample that you should have recovered. Do the same thing for cyclohexane, 20 divided by 50, and the same thing for toluene, 20 divided by 50. And this gives you actual percentages of each one of those components. Finally, to calculate the percent error over here to the side, you need to relate your percentage to the actual percentage. So again, theory minus actual divided by theory. And your percent errors could be negative or positive. Typically, we always provide them as a positive number because all that the sign does is means you're on one side of the error or the other. You're either too high or you're too low, and that we don't really look for. We just look at the overall error that's associated with the numbers. So 18.3 gave me an 8.7% error. When I use the actual total volume of 50, it looks like my error goes up, and it almost doubled here this time to 19.7, right? Cyclohexane, this person, if I use the recovered amount, received a 2.99% error. And then when you compare that to the total of the 50 that you should have gotten, it actually goes up by a factor of almost, 5 times, right? And then you do the same thing for toluene. This is based off of your recovered 7.35, and then what it should have been off of 50, which was 5.60% error. So overall, that is the spreadsheet, and that's what it looks like for the fractionation lab. All right. So refractive index column is needed. The total number of milliliters that you have collected from your graduated cylinder is needed. Then your refractive index calculations will be used to calculate the percent of acetone, the percent of cyclohexane, and the percent of toluene in each one of those cuts. Again, whenever you get a negative concentration here, that is a sign that you need to switch over and use the other two-component system now, because you cannot have a negative percentage. Then, once you get the percentage, use those percentages to calculate the actual number of milliliters of each component in the fraction that you have collected. And you do that for all three components all the way down the spreadsheet. Finally, you sum them all up, and then you compare them to the known values by calculating percent error. All right, so if you've got questions or if you need help with the spreadsheet, you know where to find us. We're more than willing to sit down with you and kind of help you churn out these numbers, especially when you start plugging them in and you're seeing that something's not really coming out the proper way. So keep that equation handy, because not only did you have to use it for the pre-lab, but you're also going to have to use it for the spreadsheet, which is here. The good thing, though, is that once you get a line item completed, only thing you've got to do is click this box in the bottom right-hand corner and drag down. And when you do that, it will follow that calculation with you through all the cells. So that will prevent you from going in and typing in that equation every single time. Do it once and then let Excel mimic it by copying and pasting it all the way down. And that's how you do it. Click the box and drag it. So again, if you've got questions, you know where to find us.